In this segment, I'm going to talk about the properties of quadrilaterals, or four-sided closed figures, and we're going to use these properties to help us classify them into the different subcategories of quadrilaterals. So a quadrilateral is any four-sided closed figure. So if I want to make 1, 2, 3, 4, that would be a quadrilateral, and no matter how I move it, as long as it's closed, meaning that there's no open spots that things can get out, these would all be quadrilaterals. Four-sided closed shaped figures. Now there are some quadrilaterals that we're more familiar with, and so we're going to talk about the familiar ones, and we'll get to some of the more obscure ones here in just a minute. So I'll get rid of these, and we'll get one that we're more familiar with first. So here we have a parallelogram, four-sided closed figure, and it's called a parallelogram because its sides are parallel. Its opposite sides are parallel. So LM is parallel to JK, and MK is parallel to JL. And if I grab onto it, that's still going to be the case. The one on the left, the side ones, are parallel, on the ones on the right are parallel. And I can get the computer to help me out with this. I can show that lines are parallel if they have the same slope. So I'm going to have the computer show us the slope just to mathematically show us that they're parallel. And so it's telling me that the slope of this one is 0.042 and the slope of this one's 0.042. The ones on the right and the left are 1.89. And if I drag a piece, we still see the top and the bottom are the same, and the left and the right are the same. And it doesn't matter how I shape this, the ones top and the bottom and the left and the right are now the same. Of course, these ones are now here and here, and these ones are now here and here. But the opposite sides slopes are parallel. That's why they call it a parallelogram, because the opposite sides are parallel. So it has two pairs of opposite sides that are parallel. And that's often all we talk about when we talk about making that, but I want to show a couple other things. Let's talk about the diagonals from the bottom left to the top right hand corner and the top left to the bottom right hand corner. So I've drawn them in, and they crisscross here at this point A. This is our intersection point. And now I want to point out a couple of things. Do the crisscrosses cut them into equal size pieces or not? And so I'm going to get the computer to measure those for us. And we can see that this diagonal cuts this diagonal exactly in half. This length is 1.306, this is 1.306. And the other diagonal cuts it in half, 0.6, 0.6. And so we notice that the diagonals bisect each other. And if I change it, I still notice that these ones are 1.96 now, but these ones are still the same. And if I bring it around, the same thing happens when I do this. These ones are the same, and these ones are the same. So in a parallelogram, not only are my opposite sides parallel, but my diagonals bisect each other. They cut them into exactly half across. Now, that's typically how we see a parallelogram, but if I do this, and I pull it so that it goes like this, is this still a parallelogram? The opposite sides are still parallel to one another, and now my lengths are getting very, very similar, and if I play around with it a little bit more, I can make something that all four sides, well, that's pretty darn close, all four sides are exactly the same. Is that still a parallelogram? Well, the opposite sides are parallel, and the diagonals still bisect each other. Those are the definitions of a parallelogram. It's four-sided, two pairs of opposite sides being parallel. So this shape is also a parallelogram, but it's something we don't usually call a parallelogram. We call it a square. The next one I want to talk about is the rhombus. And if we look at these two side by side, they look pretty similar. And so a rhombus is like a parallelogram, but a rhombus has a special characteristic that a parallelogram doesn't necessarily have. Remember, a parallelogram, opposite sides parallel, four-sided figure. That's all we really need to say that it's a parallelogram. So this one has opposite sides whose slopes are the same. They're parallel, and top and the bottom are parallel, and therefore this would be classified as a parallelogram. Well, why does it get a special name? Well, it has its own special characteristic. So like the parallelogram, its diagonals bisect each other. So E to H is cut in exactly in half, so EB is the same thing as BH, and GF is cut in half, so FB is equal to GB. So again, if it's a parallelogram, its diagonals must bisect each other. So how is it different? Well, it's not the diagonals that are different, it's the length of the sides. So I've asked the computer to measure the lengths of the sides, and so we know it's a parallelogram, but remember when we did a parallelogram, its sides could be all sorts of different lengths. And so when we take a look at our rhombus, we're going to take a look at our sides being all the same. And if I change one of them, they all change to the same length. The opposite sides are still parallel to one another, and the diagonals still bisect each other, but the sides are exactly the same length. So a rhombus is a special parallelogram that has 4 equal sides. So here we have another quadrilateral that we're quite familiar with. We call it a rectangle. And a lot of people think it has something to do with the lengths of the sides. But really the definition of a rectangle is a quadrilateral with 4 right angles. And to get 4 right angles automatically produces something that looks like this. I can't take a piece and drag it over anywhere that doesn't get a right angle, and as soon as I do get a right angle, then I always end up getting my rectangle shape that we're familiar with. So a rectangle is a 4-sided figure that has 4 right angles. And this idea that the opposite sides have to be the same length really isn't important. A rectangle is just a 4-sided figure, a quadrilateral, with 4 right angles. Now because we have 4 right angles, the opposite sides would have to be parallel because they're at 90 degrees. So these are vertical on the sides and these are horizontal across the top and the bottom. And if I tilt it, it still works the same way, except they're just not going to be horizontal and vertical. That's going to be having the same slope, and so will that. But that's a byproduct of having 4 90-degree angles, not because of anything else. Now my diagonals also bisect each other, so the distance from R to C is equal to the distance to C to N. And the distance from Q to C would be the same thing as C to P. But when we notice this, we say, well, wait a minute, what else do I notice? Well, not only do the diagonals bisect each other, but they're all exactly the same length. Each of these diagonals are the same length, and each of the pieces from the corners to the center are all the same length. So that's another characteristic of a rectangle. Actually, we'll find out it's also the characteristic of a square, and that's because they also have 4 right angles. And we'll talk about that in just a sec. So here's our rectangle that we're kind of familiar with, but if we notice, if we bring this across, it's still all rectangles, opposite sides are parallel, all those kinds of things that we think of, but it's still a 4-sided figure with 4 right angles. And as I bring it across to this, I also get something that looks familiar. So this is a square. So therefore a square has all the properties of a rectangle, but a rectangle doesn't have all the properties of a square. A square has one more set of instructions that have to be met to be classified as a square. So here's our square. Our square is a parallelogram. Remember, a parallelogram says we have opposite sides that are parallel. Well, its opposite sides are parallel. It's a rhombus because a rhombus says the opposite sides have to be equal, and its opposite sides are equal. It's a rectangle because it says we have to have 4 right corners, and it has 4 right corners. What makes it unique from the rectangle, however, is that its 4 sides are all the same length and they're all right angles. A rhombus has 4 sides equal, but the angles aren't the same. And a rectangle has right angles, but it doesn't talk about the sides. So a square is kind of like both of these. Opposite sides parallel, it's got 4 right angles, and its sides are all equal. And just like our rectangle, our diagonals bisect each other, and that all the diagonals are the same length all the time. So square is a very special kind of figure. And as you can see, the criteria that are necessary We started off with a four-sided figure, any four-sided figure, then we went to a parallelogram, then we talked about a rhombus, then we talked about a rectangle, and then we're talking about a square. So there's characteristics that are necessary to be classified, and as we get more further and further down our classification chart, there's more and more characteristics that need to take place and need to be met. Now talking about this shape, it's called a trapezoid. It's not the more familiar one. A trapezoid is a four-sided figure, so it meets the criteria of a quadrilateral. It has one pair of parallel lines and they're opposite. So the opposite sides are parallel. Now depending on what book you're talking about, sometimes you say it might be read as at least one pair. So if these two sides were also parallel to one another, it could be classified as a trapezoid. But I'm going to say that it's exactly one pair. So the one pair of opposite sides are parallel to one another, and we're going to call that a trapezoid. I've created some diagonals, and we can see that where the diagonals, well, we don't have to do the intersection point, but we can put that in there. From C to B is a different distance than A to D, and we can squish that around a little bit and notice that those distances don't have to be the same distances. And so they don't bisect each other. D to E is much shorter than E to A, and C to E is much different than E to B. So there is no specialness around a trapezoid other than it's a four-sided figure and one pair of opposite sides are parallel to one another. Here's another quadrilateral. It's called a kite, and it's in the shape of what we would typically call a kite. We put a little tail on the bottom here, and that would be our kite. And it's also a quadrilateral, and it also has some characteristics as well. Its sides don't have to be parallel to one another. Their slopes aren't the same. Nothing seems to be parallel, so that's not the thing about the kite. The thing about the kite is that adjacent sides are going to be equal. And again, depending on which book you're looking at, sometimes it says at least two sides or exactly two sides have to have sides that are equal. So I'm going to just show some measurements here. So we can see that GH is 0.9 and FH is 0.9, and so those two are the same length. We can also see these two long sides are the same length of 1.46, and we can make sure that when we change the shape of this still holds true. But again, it's not opposites, they're adjacent. So pieces that are touching, they're both touching at H, so these two are called adjacent because they touch, and these two are called adjacent because they touch here at E. So a kite has two pair of adjacent sides that are equal to one another, of the same length. And showing also that when we put our diagonals across from the bottom corner to the top and from the top down, the diagonals clearly aren't the same length. But when I do put my diagonals, it does bisect the short side. So this distance here and this distance here are the same. And it doesn't make any difference if I change the shape of my kite, that case is going to be true. So the short side will all be bisected, and if I stretch it out so that it looks kind of really long and stretched out, it still is going to hold true. So in our kite, we have adjacent sides that are equal, and our short diagonal is bisected by the other diagonal. So we've talked about a variety of shapes, quadrilaterals, and some of their properties and characteristics that could be used to classify them. And the confusing piece is some shapes have multiple characteristics that have something in common, but something slightly different. So we have this nested idea of more and more and more criteria that need to be met to meet the criteria of a square. And that happens in a couple of different shapes, and just to show how that works.